All right, so this video is meant to be a tutorial of energy graphing and what these graphs actually mean for chemical reactions. So I'm going to go through number 4 of our practice from yesterday or from Tuesday, and we're going to go through how you would approach a question like this. So let's get started. Okay, so number 4 reads, your cells transform sugar molecules into energy that you can use. That energy is then in turn used as fuel for your body. The chemical equation for this reaction is, and it gives you this one. Okay, so C6H12O6 plus 6 CO2 or plus 6 O2 equals 6 CO2 plus 6 H2O. Okay, so sugar plus oxygen is going to yield carbon dioxide and water. Okay, then we get a data table. Okay, when you see questions, I'm going to make this a little bit bigger so you guys can see it better. Okay, so when you guys see these kind of questions and you get a data table, the first thing that you should do is start making your graph and plotting the points. And this is a lot easier than it seems. First thing you want to do is set up the axis. Okay, so we said in class the energy stored in the molecules is always going to be on the y-axis. So right away, you always want to put energy here on the y-axis. We always know that percentage of reaction complete is going to be on the x-axis, so I'm going to put that down here. Okay. Then we have to set up the scale for our axis. That just basically means writing in the numbers. So I'm going to go by 20s down here on the bottom because that's what we go by here, and it's uniform, right? We go 20, 40, 60, 80, 100. 20, 40, 60, 80, 100 down on the x-axis. Now on the y-axis, because this is a Word document, it was kind of hard to get the numbers completely perfect. So I'm just telling you this, each slash is 10. Now on a test or in a lab, you would definitely need to indicate that they're 10 each, but I wasn't able to do that in this document. But you guys know 10, 20, 30, 40. Okay, once you have it set up, all you have to do is plot the points. So we just have, let's see, 6 points to do. So let's start with the first one. At 0% complete for the reaction, so 0 on the x-axis, we know that there's 40 kilojoules stored in the molecules. So let's go down here. At 0%, okay, we have 40 kilojoules stored. So that's the star right here. First point. Second point, we've got at 20% of the reaction, we've got 45 kilojoules. So it went up a little bit. So here we go, 20% of the reaction is complete, and our energy now has risen to 45. Okay, at 40%, we rise up to 55. At 60%, now we're at 60. At 80%, now we're down to 30. And then at 100% of the reaction, our energy in the bonds is 15. Okay, great. Let's talk about what this actually means. So we're talking about energy in bonds, okay? And it seemed like people were confused today, so I want to be really clear on what I'm talking about. We said that the reactants, if we look at our chemical equation, the reactants in this example are glucose, which is this molecule, C6H12O6, and oxygen, which is this molecule, 6O2. Okay, so that means we have 6 of these ones, and we've got 1 of these ones. Okay, so we've got 6 of these guys. I only put 1 because it would be too cluttered, but we've got 6 of these and then 1 of these. So what we're saying is that at the beginning of the chemical reaction, there is 40 kilojoules of energy stored in these molecules. So stored in the bonds of these molecules in the reactant side. Okay, then we know the products of this chemical reaction are 6 molecules of CO2 and 6 molecules of H2O. So I put pictures down here. So this would be H2O. This is only showing 1, but there's 6 of them. And we have CO2 also, 6 of these also. So what it's saying is, if we read the graph, the products only have 15 kilojoules stored in their bonds. So we started with 40 stored in these guys, and then after the reaction ended, we had 15 in these guys. Okay, so 40 and 15. So you want to conceptualize this maybe like money. If you start out with a bunch of money, say you start out with like 40, this is way more than 40 bucks. Let's say 40K. Okay, so $40,000 at the beginning. And then at the end of your day, you only have 15K or $15,000. You're going to be like, what the heck? Money doesn't just disappear. It had to go somewhere. It's the same thing for these molecules. These guys are like, man, what the heck? We started with all this energy. We had 40 kilojoules of energy, and now we only have 15 over here on the product side. So what the heck? It had to go somewhere, right? It doesn't just disappear. So we say that energy was released. So anytime you have more energy in the reactants and less energy in the products, the energy we say was released. Okay, so when I say released, it means released into the areas around the reactant. So around where the reaction's happening, the energy is released into the atmosphere. This would be like the explosion we saw. When you have a combustion reaction, the energy is released in the form of an explosion. Okay. Okay, we also got this activation energy thing here. So it says label the activation energy portion of the graph. Okay, so activation energy, we said in class on Tuesday, is the energy you need to get the reaction started. Okay, we said that. So why do we need that? Well, we have to break up these molecules because a chemical reaction is when the molecules break up and then form new ones. So to break these guys up, we have to add some energy. So that's what activation energy is. You're adding energy to activate the reaction or break up the bonds. Okay, you have to do that because you have to break them up before they can form new ones. So activation energy is the area between the beginning over here and then all the way up to the highest point of this mountain, I guess you could say. Then it asks you label the reactant portion of the graph and the product portion. Okay, so I'm gonna just add a little text box. Let's see if we can get that to work. I have to move my face. Okay, we'll add a little text box. Okay, the reactant portion is anything on the left side. So I'm gonna add that here, reactants. Okay, to the left of the hump. And then everything to the right is the products. Okay, so anything to right is indicating the energy in the products over here, so the energy in these bonds. And anything to the left is reflecting the energy in these bonds. Okay. Then the last question was more of like an extension, like let's think about this reaction like more critically. It says, why is it important that energy is blank in this reaction? Okay, so I'm going to change this already to released because we know it's released. Okay, why is it important that energy is released in this reaction? Okay, and to answer this question, I have to move my face again to bold it. Okay, so to answer this question, you have to kind of look back at the information that I gave you at the beginning. So it says your cells transform sugar molecules into energy that you can use. That energy is then in turn used as fuel for your body. Okay, and then it gives you the chemical equation and you do all this work that we just talked about. Think about it this way. The whole point of this reaction is to give you energy. Okay, so you're basically trying to get the energy out of the glucose molecule. Because if you guys remember, we eat food, right? We eat carbohydrates, which are sugar molecules. And the whole point of eating that is to get the energy out. Okay, so that's how your body does it. You guys have this chemical reaction going on all the time, right? Even as we speak right now, you're breaking down these sugar molecules, forming these new ones. And then in that process, you're getting all this energy out. You're releasing energy. This energy that's released is in turn used for you to function. So that's kind of the point of this reaction. I hope this was helpful. Feel free to watch this over and over again as much as you want to. I will put this on my website and yeah, study hard. Okay, bye.